afternoon. That is Dr. Robert Baker. Robert Baker is an assistant professor in chemistry in the Trinity College in Dublin. His research interests are in the fundamental and applied of actinide chemistry, and in particular the use of neutron diffraction and spectroscopy to the study of the structure and electronic of thorium, uranium, and neutronium complexes. And Rob will be talking today about the study of uranium minerals. And I'm going to stop sharing my screen. And Rob, if you want to share your screen when you're ready.
Okay, thank you very much, Sophia, and thank you so much, everybody, for the invitation to talk and to be able to show how bad I am at using Zoom. Okay, here we go. So I hope to give you a talk today on X-ray spectroscopy and some of the work that we've been doing looking at uranium minerals. So it's always the point where the speakers struggle to get their things working, but here we go. So thank you very much for allowing me to talk about some of the work that we've been doing. And I want to do the first slide first, which is the most important, which are the acknowledgement slides. So from a theory point of view, I'd like to thank Piotr Kowalski and his group at ULIC for all of their help in the theory, and Ping Yang at LANL as well for some of her help. But for the X-ray spectroscopy, this was started by my PhD student, Aurora Walsh, and has been really taken off and driven by Sam Edwards, who's in the virtual audience at the moment. We've worked closely with Tonia Vitova and her group at INA in Karlsruhe. And I'd like to especially thank Ivan and Elke for helping me with the Neptunium experiments that I'm talking about, specifically to make sure that I left Karlsruhe with the same amount of Neptunium in my body as I started off with. I'd like to thank the people at Diamond as well, especially Fred at I-18 and I-20 and Burkhard and his team at I-08. Christina in ESRF has been very helpful, as has Eugen Welschke in BESI 2 for some of the other spectroscopy that we've been doing. But I really want to thank Calypso Plus as well for funding our trips around Europe. So to orient everybody, we're talking about uranium at the bottom of the periodic table. These are radioactive and have funny shaped F orbitals, but in general, not many people come down to this area of the periodic table. But if you do, there are an awful lot of interesting chemistry that's going on. For example, small molecule activations, different oxidation states, activation of inert bonds on the uranium complexes, and some really unusual magnetics as well. But maybe for this audience, what's more interesting is how you can use X-ray spectroscopy to probe the electronic structures of some of these incredibly radioactive materials that are further away from americium. And so Thomas Albrecht-Schmidt and his group have shown that you can actually make curium, berkelium, californium complexes and structurally characterize them. And Stosh Kozimor and his group at LANL have shown that actually X-ray spectroscopy can be used to probe F element or F orbital covalency in simple metal hexachloride 8 species. But probably what's even more impressive has been the recent report of Einsteinium complexes. This is the L-edge Einsteinium edge spectra measured on 175 nanograms of Einsteinium. Mainly because some of these have eye-wateringly scary numbers for the radioactivity. 13 milligrams of berkelium for these complexes was 777 gigabecquerels. And Einsteinium is just this massive scary number. To remind everybody, a becquerel is a disintegration per second. A terabecquerel is 10 to the 12 disintegrations per second. So going back to some maybe first year chemistry, a key difference in F block metals comparing the lanthanides to the actinides is the participation of the F orbitals in bonding. So for the lanthanides, the 4F orbitals are core-like, whereas for the actinides, the 5F and the 6D orbitals extend out far enough from the nucleus to be able to be involved in bonding with ligands. And this idea of covalency is something that is becoming really important in in looking at bonding of actinide complexes, for example, for speciation controls or extractions for nuclear fuel cycles. They have many more different oxidation states than the lanthanides, but one of the differences between everything in the actinide series is the +3 and the +4 oxidation states normally have a spherical cation, such as you would expect for transition metals, whereas the higher oxidation states have these linear actinyl units where there is just definite covalency and orbital overlap in the uranium to americium and oxygen bonds. But as we go across the series, the d orbitals increase in energy and the f orbitals decrease in energy. So around uranium, we have the point where the d and the f orbitals are about the same energy. So we start to get hybridization involved as well, which means that trying to understand electronic structures becomes really quite challenging, to say the least. For an applied perspective on this, then of course, nuclear waste is the big selling point. So the UK's nuclear inventory in 2120, assuming no new builds, will be around about 3 times the volume of the Royal Albert Hall. And again, another scary large number of radiation load. And the majority of this radiation load, the 78 billion terabecquerels of radioactivity, comes from the fission products, plutonium, and the minor actinides. The big problem with plutonium and the minor actinides is their long half-lives. So a ton of uranium produces less than a bag of sugar of neptunium, americium, and curium. But this and the 9 kilos of plutonium cause a huge problem for what to do with the waste. So at the moment, the current thinking is a geological repository where this will be buried underground and stored away from the environment and from people. But these long half-lives are a real challenge. So to put 10 to the 3, 10 to the 7 type numbers in perspective, if we go back in time for one half-life of plutonium, that's when the pyramids were built. And if we go back in time for 10 to the 7 years, it's about when the dinosaurs died out. So these are really challenging experiments to be able to do because of the timescales involved. The majority of waste in the UK, in Europe, are going to be in a globally reducing environment underground. And they're going to be probably stored in stainless steel containers with certain degrees of backfill. But over a long period of time, of course, water will eventually ingress into this. And because it's radioactive, this will generate hydrogen peroxide. Hydrogen peroxide is then a really good oxidizing agent to oxidize these complexes, which are generally in their +4 oxidation states as the oxides, to something that's more soluble, which can then move through the environment. Maybe these can move via hydrolysis to form colloids. There are problems with the stainless steel, which won't be stainless over these periods of time and generate iron sites for reduction. Or we could have maybe the incorporation of these radionuclides into new phases that are formed on the surface of spent nuclear fuels. So this can either retard or enhance mobility to the environment. So it's a really complicated situation. If we think about actinides in the environment, we should be able to use those as models for what might happen. So for uranium, the most stable oxidation state is its uranyl, this dioxo uranium compound. But under certain circumstances, certain pHs and EHs in the environment, these precipitate out as uranium minerals. So maybe we can use these uranium minerals to look at what happens for the oxidative weathering of uraninites for decomposition of spent nuclear fuels. For the other actinides, that's a bit challenging to do because they were only discovered and synthesized in the 1940s. But here is a nice, in the wrong term, the word nice, environmental study from the US. So this is the Hanford site in Washington State. Here was the site of the very first nuclear reactor that was built, and not for commercial power generation, but to generate plutonium for the war effort. And it has a slightly checkered environmental history. So in this area, for example, somewhere between 7,000 and 8,000 kilos of uranium waste was spilt in one overfill event in the 1950s. So this waste was stored in single-lined tanks that are buried underground. Record keeping wasn't quite so good, so they still have no idea how much was spilt. And this is now going close to the Vado zone of the Columbia River. But using some X-ray spectroscopy, it's been shown that uranyl carbonates and uranyl silicates are the speciation controls here. In another area, somewhere between 33 and 59,000 kilos of uranium was disposed of over the lifetime of the site. And at some point, somebody decided adding copper was a good idea to control the redox processes. So now the uranium chemistry is dominated by these copper uranyl phosphates and copper uranyl silicates. Just to make things even more interesting, sorry, wrong way. This is the area where the plutonium was processed, firstly from the power station, and there's about 436 terabecquerels of plutonium and over 1,000 terabecquerels of americium disposed of as americium waste, as liquid waste. And just to make things even more exciting for people living in Washington State, there are also 980 terabecquerels worth of technetium stored. The speciation of this is unknown, but is a real problem because this can't be vitrified into glasses, because this could form technetium pertechnates, which are then will evaporate in the process of making it into a glass. So it's a bit of an environmental mess, but it is a good place to study what happens for actinides in the environment. So if we go back and think about what happens to uranium, the oxidative weathering of uraninite, all of these minerals, which have names a little bit like diseases, have been formed and can be mined from uranium mines or seen on the surface of spent nuclear fuels and uranium oxides. One interesting one is this mineral studtite, which is formed by the reaction of any of these minerals or uranium oxide with hydrogen peroxide. And it forms this linear chains which are linked by peroxy linkers. Now, these minerals can incorporate radionuclides. For example, becquerelites could exchange calcium for strontium, radiostrontium, or radiocesium, or it can be incorporated, or neptunium can be incorporated into the interlayer cations, or even into the sheet structures. So this might show ways of retarding mobility of migration. So we can use X-ray spectroscopy, hopefully, to take advantage of the fact that we don't need very much of our radionuclide materials to look at exactly what happens. To start off with, we really want to benchmark our studies on the basis of the natural minerals. So to understand the spectroscopy, this is the MO diagram for a uranyl ion. Okay, so this, we have some semi-core involvement of the 6p orbitals, which means that unusually the sigma orbitals are higher in energy than the pi orbitals. But this is where this covalency comes into effect, forming the uranium-oxygen bonds. And we can use a number of different edges in theory to look at both the d and the f orbital contributions to bonding, as well as the ligand-based k-edge spectroscopy. So the commonly used L-edge probes d orbital occupancy, M-edge probes f orbital occupancy. And using some high resolution XAS, we can now start to resolve features in particularly the M-edge that you can't really see using conventional spectroscopy. And this is because of this is important because you get less core hole broadening in the M-edge compared to the L-edge. So we'll start off by looking at studtite. This was this unusual mineral. And it has very unusual but very important thermal decomposition characteristics. So at about 60 degrees C, studtite loses these two waters of coordination to form metastudtite. Heating this up forms another phase which is amorphous, which has only very, very recently, like in the last month or so, been studied by X-ray spectroscopy. But some work on neutron studies suggests that it might be U207. This is important to understand really because this species, whichever it is, reacts with water to generate oxygen. And this results in pressure buildup in drums of stored waste. So much so that there have been 3 or 4 accidents in the US where people have actually incorporated uranium into their bodies, which is never a good thing. And also studtite can incorporate neptunium via some unknown mechanism and then release both neptunium and uranium into aqueous solutions. So this again suggests that this might be a way of firstly retarding and then maybe even enhancing neptunium and uranium migration in the near field. So we were able to synthesize studtite and metastudtite in the lab really easily. And what's really surprising as a coordination chemist is the difference in the colors, which is also shown in the band gaps from the UV spectra, because all we're doing is removing these waters of coordination. So how can you change something so drastically by just changing the coordination waters? So we started looking firstly at the structures of these compounds. Now, as everybody does, you go to a mine in Zaire and dig out a crystal and stick it on your diffractometer. And this happened, and the X-ray structure of studtite has been reported. These are the NEXAFS studies from our synthetic studtite, and they match pretty well with the spectroscopy, with the X-ray structures of the natural material. But metastudtite has never been structurally characterized. And what we see from our NEXAFS is that there's a slight increase in the UO bond length, which is about in line with the error of the measurements, but a distinct shortening of the UO peroxy bond. So this was the first structural characterization of metastudtite. We've always used powder XRD to check purity, but eventually we found somebody to do Rietveld refinements. And what was really interesting from metastudtite is that it seems very happy to bend the uranyl. Now, I said earlier that the uranyl ion is covalent, so bending a UO double bond is really quite tricky. And there are very few examples in the literature where this has happened. But we see from our refinement that the bend is about 168 degrees, so quite far away from linearity. Now, of course, you shouldn't put all your eggs in one spectroscopic basket or structural basket. So we've tried to look at this in more detail because this is really quite unusual. But before we get to that, here are the high resolution Zane spectroscopy that we measured at ENA quite a few years ago now. So there are 3 features: this pre-edge feature, the main feature, and then this post-edge feature here. And fitting this data using FEF calculations, we can get to the density of states plots. And what's really nice is that we do see a change in both the oxygen and the uranium D and F orbitals when we remove those waters of crystallizations. And the change is 1.3 EVs from the theory, which is pretty comparable to our experimental results. But what's even nicer are the M-edge spectroscopy. So we can clearly see 3 transitions, which can be assigned to the transitions to the 5F orbitals in their delta and phi types, the pi star, and then the sigma star orbitals. You also note that there's this small transition here, which is not reproduced in any of the calculations we have done. We're not really sure what it is either. But we can see that there's a shift in the 5F sigma star transition. And from some assignments that were done by Tonya in uranium, neptunium, and plutonium complexes, this shift says that there's a change in the covalency of the UO bond. And this is the change in the overlap-driven covalency, so how the F and the P orbitals overlap with each other. So when we remove this water of crystallization, we change the covalency of the UO bond, which again is really quite surprising. If we leave metastudtite in a cupboard in the beamline for a while and then come back to it after 20 months, we can see that the studtite actually dehydrates to metastudtite. And this fits with some of the thermochemical data that was reported previously, where metastudtite is actually more thermodynamically stable than studtite. That's about as far as you can go by looking at MO diagrams. So we wanted to look in more detail using some computational studies. So in collaboration with Peter Kowalski, we benchmarked our powder patterns against a number of different density functional theories, and we found that PBE sol plus U gave the best fit. And just to confuse everybody, this U doesn't stand for uranium, it's the Hubbard U parameter. So one of the problems with this is that the bond lengths are not quite as reproducible as the electronic structure, but this is a limitation of the technique. But even so, we do seem to get pretty good fits with the from the NEXAFS data. These are the DFT density of states plots, and we can already see in red the F orbital contributions, which look very similar to our M-edge spectra. What we can do in silico now are things that we can't really do experimentally, and we've bent things and elongated things to see what happens to the spectra. And I draw your attention again to this sigma star transition, because this seems to be the one that's only sensitive to any changes in the structures. And this seems to be sensitive only to the uranyl bond length, not the equatorial bonds, which are expected, but not the angle either, which is quite unusual and a bit of a surprise. So we can't really probe the uranium oxygen in any more detail using the uranium side. So what about the oxygen side? So these are the density of states plots for studtite and metastudtite on the oxygen edges. And you can see that from the theory, at least, there are some shifts that we may be able to resolve using oxygen K-edge measurements. So can we use oxygen K-edge spectroscopy to observe differences in covalency? And can we confirm the bending? Now, we've never been able to grow single crystals of these compounds, so we haven't been able to use more conventional soft X-ray spectroscopy under vacuums. So we were able to actually do these measurements using the STXM beamline at Diamond. So this is, if nobody's ever used it before, this is similar to SEM and TEM, but rather than using electrons, we use X-rays. For this, you need small particle sizes, which is great for our radioactive protection or radiation protection ideas, but they're element specific, and we can get spatially resolved maps. So this means we could possibly use this for environmentally relevant samples now, and even for things like nuclear forensics, which is a big buzzword in the US at the moment. The problem was our sample preparation, and this is the hardest thing I think my PhD student has ever had to do in his life before. So we had to just put small amounts of sample on these TEM grids, and then for radiation protection reasons, sandwich them with a second membrane. This had to be done under a helium atmosphere to make sure we didn't have any oxygen in the sample from the air. We tried a number of ways to be able to do this, because sandwiching these using epoxy resin was really, really tricky. I don't know whether my camera is good enough, but this is one of the 3D printed sample holders that we use. And if you can just about see, the sample fits in that really tiny hole here. So I hope this gives you an idea of the scale it fits in there. So it's really, really tricky to be able to manipulate. And it turns out that this was just not good enough to get a good seal. So we eventually milled something out of Teflon, and were able to get the samples prepared and sent to Diamond after a few stops and starts. And we did actually manage to measure some spectra. So this is the oxygen K-edge spectra of studtite and metastudtite. So if we look at our MO diagram now, we should expect to see 3 or 4 transitions, one to the pi star U, the sigma star U, and the pi star G. We should also see this guy here as well, but nobody in the literature has really ever seen it before. So if we look at this with a bit of eye of faith, you can see that there are 3 transitions in studtite and metastudtite, and curve fitting for these, we get positions A, B, and C, which don't really change very much compared to the 2 of them. And they're pretty close to examples in the literature of well-defined species as well. So this was rather disappointing, but when we overlaid the fitted peaks, what we see is that this transition here is much broader in the metastudtites compared to the studtite. And this is something that was also observed in these 2 complexes as well. We chose the cyano complex because this has anti-bonding CN molecular orbitals, which can get involved in the bonding to the uranyl as well. And we have exactly the same situation with our oxygens from the peroxy species. So looking at our MO diagram, we could assign this peak to the transition to the pi star U, this one to the sigma star U, and this one to our pi star G molecular orbitals. But we already have the theory to look at this. So does this fit with our theoretical ideas? And looking at the density of states, we can see that this guy and this peak has uranium contributions. This one doesn't. And it's only this one that has peroxy contribution. So maybe we should say that this is the pi star U and the oxygen peroxy pi star orbitals. This one is the sigma star U, and this one may be the pi star G, but it doesn't have any uranium contributions, so it must be just water. So this one, really, everybody knows what a sigma star U orbital looks like in a uranium complex, right? So this is the cone-charm canonical orbitals for a uranyl ion, okay? And you can imagine that if this bends, then it does change the, you could see a change in the intensity of these transitions. Or it could be the fact that the peroxy groups are actually getting involved in the bonding. And so how can you tell the difference between these two? And this has been a real challenge for theory. But eventually we were able to get pretty pictures because we're just simple coordination chemists, not theoreticians. And these are the density plots for this transition. And what you can actually see from this is that this is the sigma star molecular orbital from the peroxy with a uranium type orbital. So the pi star orbitals are not actually involved in this at all, which is somewhat of a surprise again. This pi star U orbital looks to be mainly based on the uranium. And then finally, our assignment as the pi star G is completely wrong, and it's certainly just water. But what you can actually see is the lone pair of electrons on the peroxy interacting with the hydrogens on the water. So this is a picture of the hydrogen bonding network in studtite and metastudtite. But what gives us the best clue is actually if we take our bent metastudtite and plot the density of states, and you can see that it starts to split. So we think now that what we have here is evidence for a bend in the uranyl bond. So this is really clear. I think this is our interpretation of our data, that dehydration, so removing that water of crystallization, actually bends the uranyl bond. This kind of fits with what we had previously from the NEXAFS data as well, where we see a shortening of the UO peroxy bond. So that kind of fits with our pictures here, where we're having interactions with the sigma star orbitals. So this is kind of like classical and non-classical dihydrogen complexes from transition metals. And we've also reduced the covalency in the bond from the M-edge spectra. Just to show you some how these change compared to conventional K-edge spectra, we were able to measure cuprous-glodovskite, which are these crystals, and this we bought off eBay. So there is a whole range of compounds you can buy off eBay, and this is the copper uranyl silicates. This was measured at BESI and the normal K-edge data, and you can see that there's a bit more resolution in this compared to here. And Ping Yang at LANL is looking at the theory of these complexes. And again, the energy separations in some of these are 0.1 to 0.2 EVs, so a challenge for theory. But going back to our experiments at Diamond, what was really nice is we could look at the soft edges. So this is the N6-7 edge. So this is the transition from the 4F to the 6D. This, I think, is the first time anybody's measured this by STXM technique, and it should be complementary to the L3 edge spectra because it ends on the D state. Much less core hole broadening, so maybe we could use this to probe crystal field effects. This red dotted line is the theory. So in certain circumstances, you think that this looks like it fits really well. However, we have problems with theory because it's really difficult to treat core orbitals of periodic systems which already have substantial relativistic effects, and spin orbit and crystal field splittings are about the same. But if we overlay our N67 and L3 edge spectra, you can see that they do seem to give us complementary data. And we think this is a really exciting use of STXM. Not to dwell too far on this, but we've been able to measure some valence to core spectra on these as well with Fred's help. And it seems that selecting the excitation line gives us better spectra if we go to the one that has the lowest transition probability. We haven't gone into too much detail in this, but for studtite at least, we can see the differences when we plot our density of states versus the experimental data. These samples seem to be, so this is, sorry, the U207 phase, which certainly looks more like a uranium-4 compound than a uranium-6 species. So we've benchmarked our samples against the uranium species. Can we add neptunium to these compounds now? So this was some work that I managed to do at ENA. Mixing uranyl nitrate in these carbonates gives a yellow crystals, which is the mineral grimselite. When you've been able to do this in the presence of neptunium, we have an emerald green precipitate instead. The powder XRD isn't very good because of radiation protection issues, but it fits quite well with a neptunium carbonate. And in the Raman spectra, we see bands associated to both uranium and neptunium. But what's the structure and what's the actual oxidation states of both of these species? So this is the neptunium NEXAFS data, and it looks like we definitely have a neptunium carbonate in a very similar arrangement to grimselite. And this is the uranium version of grimselite. So this is the uranium in the mixed phase, and this is the virgin minerals. We turned out to be quite lucky because this is neptunium rich. So we can see the neptunium edges quite clearly and the uranium edges as a smaller feature. But we can't tell whether these are mixed or phase separated. So these are the M-edge Zane spectra. Looking at the uranium first, it's certainly uranium-6, and from other work that Tonya and her group have done, we can start to get structural data from this sigma star transition. So we can get an idea of bond lengths. And this is the neptunium M-edge. So to compare with different oxidation states, it seems to fit much better for neptunium-5 than it does for 6 or 4. And again, we can start to look at bond lengths as well. So I don't want to dwell too much on this slide because I don't understand RICs very well, but they look pretty pictures. Basically from this, we can try to determine in the differences between the XES and the Zanes, how localized the F states are in these different oxidation states for neptunium-4 and neptunium-5. So what about plutonium chemistry? Understatement of the century, this is really difficult to do experimentally, so are there any models? And we came across this one. So in 1945, the first atom bomb was tested in the Nevada desert, and it left a crater of radioactive glass in the desert, which was a mineral now called trinitite. And Hermes and Strickfaden worked out the specific heat from the specific heat capacity of the soil, the temperature of the cloud, the duration of the fireball, and the yield of the bomb. And they published this in the Nuclear Weapons Journal, which presumably has a very high impact factor. So here are some pictures from where the plutonium came from. This is the Hanford site that we've already seen. Here's the Columbia River in the background. It went critical in 1944 and discharged, in September 1944, discharged in November, and processing of the plutonium began in December. This is a national monument now, so you can visit, and this is the reactor face. This picture doesn't do justice. It's about 2 or 3 stories high, and each of these little blobs that you see were where the uranium was irradiated. They were then pushed through the back face of the reactor using these rods. Because the irradiation time was short, it was pretty much isotopically pure plutonium-239, which is the one that gives you the most bang for your bucks, I guess. Here's the bomb core that was delivered from Los Alamos. you can see radiation protection wasn't quite so strict in that case. And here's the actual bomb itself. Because I've had some time on my hands, I don't know whether you can see this, but this is a 3D printed version of the gadget. And it's pretty cool because you can find these on the internet. It was lifted up on a tower to simulate an airburst because the explosive was slightly different. So in this case, rather than having two subcritical masses of plutonium which you fired together, this was a shock wave. So the subcritical mass was compressed into a critical mass. So we managed to get a sample of trinitite off eBay again. This is the gamma spectrum. So we can see neutron activation products from the soil and from the tower, but also fission products and products from the conventional explosive, which was barium nitrate. But we also see in the spectrum plutonium and americium. There have been very few studies on trinitite until quite recently, and no speciation studies at all. So nobody really knows where the actinides are or what they are. So we were able to do some measurements on I-18 and get the sample on site because the radiation protection people asked for the history of it. So we actually brought super weapons grade plutonium onto diamond. Fortunately, it's encased in a matrix, so the amount of radioactivity is tiny. And the reason really for printing this is because it's a really good way of storing your trinitite. So here's the sample of trinitite that we have. So it's not radioactive, and we got it from eBay, as you do. So here's the NEXAFS and the XRF map of part of our sample. The sample we measured was encased in an epoxy to make sure this didn't break up in transit or anything. But we see uranium, we see a lot of iron, as you might expect. Then there are spots of lead and copper as well. All of this is copper from what we found out was the curing agent from the epoxy resin. But here are the micro NEXAFS data from some of these spots. So this is the lead edge, the lead L edge, and it looks from fitting the data that we have lead carbonates, which is the mineral cerusite. And in some cases, we also see a smaller feature, which is the bismuth edge. And this makes sense from the natural decay of uranium. But in other points on the spectra, we didn't see any bismuth. So our theory at the moment is that the samples which have no bismuth were closer to the fireball than the samples that do, because bismuth has a lower boiling point than lead. The copper appears to be chalcopyrite, which is the naturally occurring mineral for copper in the Nevada desert. But the iron edge looks quite interesting. So if we zoom into the pre-edge features, it seems to be iron 2 and iron 3. And this fits with some of the course data that was done beforehand, where people just ground up trinitite and looked at the oxidation states, which were non-binary. So the iron 3 is actually the only seen in the samples that are next to the uranium. And when we look at uranium, it's actually uraninites, uranium-4, which is not really comparable with a highly oxidizing environment that happened in this case. So what we believe happens is that the uranium next to the uranium started off as uranium-6 and has been reduced by the iron-2 to form uranium-4, and the iron has been oxidized in the sample to form iron-3. That concludes what I wanted to tell you about, showing that studtite has unusual thermal behavior that we can probe by both hard and soft X-ray spectroscopy. This high energy resolution XANES and other advanced X-ray measurements, coupled with theory, shows that we can really drill down in depth at the electronic structure of these. But we're limited now by the level of theory that we can attain. And we can also use X-ray spectroscopy to give spatially resolved information on actinides complexes under environmentally relevant conditions. We were never able to see the plutonium and the americium, so this might be a limit of detection, or it might be the fact that the americium and the plutonium are not in the surface that we were looking at. So finally, thank you very much for listening to this talk. Thank you again to the organizers, and welcome any questions and comments, especially on how we can make our theory better, because that's where we're stuck at the moment. Thank you very much.
Thank you very much, Rob. Thank you for a very interesting talk showing how we normally have to use a lot of different techniques to get a whole picture of the problem that you want to solve. I don't see any questions in the question and answer box. I think Faye and oh, okay. There's a question from Mike actually. He asked, by what method was the oxygen KH and uranium NH NEXAFS detected? Thank you.
Good question. Can I remember? This was measured in IO8, and I think it was, off the top of my head, I can't remember, I'm afraid. Did the question mean whether it was fluorescence detected or not? Because this is...
I assume so. Faye, can you unmute Mike? And maybe he can... So he said the sample is behind boron nitride window?
Silicon nitride, yes. So they were encased in those silicon nitride windows. Nitrogen does come at about the same place. So we did measure a blank spectrum as well, and we didn't see the nitrogen components, presumably because these are amorphous.
Hi, Robert. This is Mike speaking. I have the ability to speak now too. Thanks. So just to follow up my question, I asked specifically that because I know, so usually at the oxygen K edge, then you would use electron yield or maybe fluorescence yield. But I think with STXM, you can do transmission. And this is what Stosh Kozimor was developing for, say, like a carbon, for the carbon case. So the problem, however, from what I understood, is that the sample preparation is extremely challenging because you can have self-absorption and things like this. So it looks like you went to a lot of effort for preparing the samples. So I'm interested in knowing how that preparation was and whether it was indeed very challenging.
Yeah, I think I broke my PhD student. Yeah, it was really difficult to do. I think the good thing was that those grids allow you to deposit just a small amount, and we drop cast them using hexane solutions. And we had to make sure that we dried the hexane solution so there was no oxygen incorporated from wet hexane as well. But then the powder that was deposited was kind of stuck on the grids with some electrostatic force. So that bit was easy, but then putting the second or the lid on top of it was the really hard bit. So on our sample holder, I don't know whether this probably doesn't make much sense, but we put the first one on the Teflon grid, and then we deposited the samples, put the glue on the top, and then, or put the glue on the inside here, I think, and then slid the top one down, let it set, and then take it out of the small holder that we had. Mm-hmm. And then, yeah, it was measured in transmission mode. And
do they damage very easily in the beam?
Sorry, say again.
Do you observe a lot of X-ray damage?
These were measured at, no, we didn't see very much in the way of X-ray damage, but what we were seeing was the studtite dehydrating slowly in the X-ray beam. So they weren't breaking, but they were decomposing, but they were dehydrating, if that makes sense. Metastudtite seemed quite stable. Now, other people have seen something very similar in even TEM and SEM of studtite, that it dehydrates quite quickly. But yeah, I think I would like to say it was a really well-planned experiment, but I think we were much more lucky than we should have been.
Well, it looks really nice. Thank you.
Thanks very much.
Christina, do you want to ask your questions? I think you're on mute now.
Oh, yes. Hi. Hello, Bob. Excellent talk. Thank you. Thank you very much. I have just two short questions. Could you please go back to the uranium RIX maps which you showed?
Yep. These ones. Yep.
Exactly. So on the right side, this is written L beta 2, L beta 5 excitation line, but the energy transfer is in order of few electron volts. So is it the energy transfer was shifted, or is it a valence band RICS?
I think this was the energy transfer. We have the valence band RICS as well, but we haven't delved in too much detail on that one yet.
Because L beta 5 is 100 eV below the absorption age. And as soon as energy transfer is only few electron volts, I was wondering if this one is the valence band, or is it really L beta 5 line?
Good question. I think I've reached the limit of my knowledge of RICS for sure.
And yeah, but no, it's in fact excellent data, by the way. And I just wonder, what was the energy resolution, if you remember, for that RICS map, which you recorded?
I can't remember off the top of my head, sorry.
Yeah, no, it's okay. Maybe my last question, if you remember how long it took for you to record this map.
It was actually quite quick, but again, we had problems with the dehydration in the beam. So we were measuring at different spots. So we were moving the sample around as well as while we were measuring it. And I think from the top of my head, it was in the order of 4 to 5 hours, something like that.
Oh, excellent. That's really excellent. Okay. That just gives us an impression about the flux and intensity, of course. Thank you very much, Bob. Excellent talk. Thanks a lot.
Thank you, Christina. Yeah, the flux we had to drop right the way down.
Yeah, so Christina, just to let you know, I-20 is a Wiggler-based beamline. We have a 1 meter Roland circle spectrometer with 6 crystals.
Yeah, thank you.
And then Tai Q Choi, if you want to ask a question.
Yes, hi Bob, thank you for your very interesting talk. Here's TQ from European NEXAFS, and I was just wondering about, one question on your oxygen KH and NEXAFS data analysis, especially the experimental one. So for the fitting analysis, have you applied the Lorentzian broadening only, or did you also consider the Gaussian broadening into this fitting analysis?
Yes, we tried Gaussian